And we're back. Had a bit of a minor issue with the camera there, so I actually filled in the rest of it while the camera was off. But what I'll do, I'll just go through it on a piece of paper as well. Okay, so next one, you see here, we have reactions of silicon dioxide, which is sand, or glass. You know, this is how they etch those exotic vodka bottles, right? With hydrofluoric acid. Hydrochloric acid is HCl, so think about it. HF is hydrofluoric. Turns into silicon tetrafluoride. That's a gas, so essentially you etch away the solid glass and it turns into a gas. Plus water, H2O. Let's balance this up. Always balance the lowest number of atoms first. So just the one silicon, that's good. 1Si, 1Si. What looks best next? Well, fluorine looks kind of easy. There's one fluorine there and 4 fluorines there. So we need 4 fluorines. So 4 HF. Okay. That leaves us with 4 hydrogens, 2 hydrogens there. 2 to the 4, 2 oxygens, 2 oxygens, it balances itself. 4 hydrogens, 2 oxygens. Okay, so that's that one. This one, you know, I did earlier, but there it is again. Okay, last one. Now this one, a little bit tricky because it involves some what we call crooked numbers. It's some odd numbers in the balancing, although what it does show nicely is the need to make sure you always have, when you do a balanced chemical equation, the lowest whole number ratio of coefficients. Okay, so let's show you that afresh, so to speak. So what we have is ammonia gas, NH3 gas, plus oxygen gas, turns into nitrogen monoxide, plus steam. Remember, steam is really just water in the gas phase. Okay. Now this one, again, the general rule is look for what's easiest first. Looks like nitrogen's pretty easy. One there, one there. That kind of balances itself. What's next? Well, save oxygen until last. Look at hydrogen here. So 2 hydrogens and 3 hydrogens. Got that lowest multiple trick, right? So 2 and 3 lowest multiple is 6. So I need 6 hydrogens both sides. 2 3s, 6 hydrogens, 3 2s, 6 hydrogens. Obviously I messed up my amount of nitrogen there, so I fixed that. There we go. 2N, 2N, 6H, 6H. How many oxygens we locked in over here? It's a bit like the normal combustion here, and it is in many ways a combustion. So 2 oxygens and 3 oxygens is 5 oxygens. So I need 5 oxygens here. It's the only place it appears. Oh, bit of an issue here because this is the only place we have oxygen, but I need 5 of them. 5 doesn't go into 2, so it's actually 2.5 times 2 makes 5. Now you can't have fractions in the balanced chemical equation, so if I multiply it all through by 2, then I get my lowest whole number ratio. So let's do that. So 4 ammonia, 5O2, multiplying through by 2, remember, 4 NO gas, and 6 H2O. There it is, same one as in the packet. Lowest whole number ratio. Remember, if you get fractions after doing the best you can, just multiply through. So you usually multiply by 2 if there's halves, multiply through to get whole numbers. Okay. Next page, basically just summarizing what we learned. So obviously be able to write a balanced equation from a word description, so names to formulas, part 1 of our 2-part process. And then once you've got that, be able to recognize what kind of reaction combination more things makes less things. Decomposition, less things makes more as things fall apart. Single replacement, one thing replaces something from a pair. And then double replacement, swap partners, two pairs swap partners. Neutralization, same, but with, as a double replacement, but acid plus base are the reactants that swap partners to make salt plus water. It's always the same. Okay. Tricks, of course. What did we learn for our tricks? Construct that unbalanced equation first. That's always the trick. Names to formulas. Once you've got those formulas right, and you know if they're right from your previous work on, you know, making the charges cancel for ionic and, you know, how names relate to formulas for molecular. Once you've got the right formulas, don't mess with them, right? That's nature's formula. They may not look right if it's not balanced, but that's because you need to put balancing numbers in front. And then you play the tennis game. So I like to call that the vertical. This is the horizontal. Do the tennis game until you get a consistent number of each kind of atom, and then it's balanced. Okay, so here's a final quick review question without showing you the answer. Okay, I'll reveal the answer in a second. So I want you to try this, okay? Combustion of ethanol. Remember the pause, right? So if you want to pause and give it a go, do that. Combusting ethanol or just alcohol. So C2H5OH liquid plus combustion, O2 gas. It's an organic, contains carbon, hydrogen, and oxygen. CO2 gas plus H2O. Remember the golden rule. You can put liquid or gas there, you know, as long as you put a state symbol. Golden rule, carbons first, 2 here, 1 there. So if you like one big old molecule contains 2 carbons, so I need 2 CO2s, 2 carbons. 5, don't forget that one. This is a pseudo-structural formula. We'll go into structural formulas later. It's kind of how the atoms run together inside the molecule. Don't forget though, 5 plus 1 is 6. So we need 6 hydrogens with our 2 carbons, not 2 carbons. We need 6 hydrogens. There's 2 inside the molecule, so 3 molecules. All right. Balance with respect to carbon, balance with respect to hydrogen. How many oxygens we locked in? 4 here and 3, that makes 4, 5, 6, 7 oxygens. Need 7 over here. Oh, there's 1 in there. Remember how I like to do this? 1 plus 6 makes 7, so the other 6, 3 times 2. And that is what I had from before. And that's as far as I got until I realized the camera had stopped working. Okay, so back to the packets now. All right. Now, next thing, and this relates very nicely to our precipitation lab, and we'll get to that math later, so don't worry about that. Okay, we'll kind of combine that math from the lecture packets with, from the lecture packets with the lab stuff. All right. So what we have here, reactions that occur in aqueous solution. So in other words, in test tubes when we dissolve stuff. Okay. So aqueous means dissolved. So we're going to write balanced equations for 4 kinds of reaction that occur in aqueous solution. Okay. Starting with probably the most popular one, which is a double replacement. Okay, so double replacement, maybe you'll write that in the side here. Double replacement. Okay. So, aqueous silver nitrate. Aqueous means dissolved. Silver, it's a metal, so that's, if you remember, that's a +1. Nitrate is a -1. Just do our math down there and forget about it. Okay, aqueous. Plus sodium nitrate, Na, +1. Sorry, sodium. Make sure I read this right. Silver nitrate, sodium chloride. It's a Cl. NaCl. All right. Yeah, okay. Silver nitrate, sodium chloride. Turns into solid, makes it precipitate, silver chloride. Now, remember, names the formulas, right? Don't worry about what went before. Silver chloride is Ag, that's a +1 ion. Chloride, that's a -1, so that makes sense. That's a 1-to-1, right? That's a solid. All right. It just so happens this is self-balancing. Okay, there's one there, there's one there. Okay, so, we'll see that in a second. Plus sodium nitrate, Na, plus 1, nitrate, minus 1. Again, good to go. There we go. Now, it's self-balancing, so don't want to worry about balancing now. There's one silver, one sodium, one chlorine, one chlorine. Now, there's one nitrogen and 3 oxygens both sides, but think of this molecular ion, just like we did when we did the whole formula thing. Think of that as a bag of atoms with a charge, right? So just count the bags. One nitrate bag here, one nitrate bag here. That makes life a lot easier. Okay. All right. That's the first one, double replacement. Next one, decomposition. So obviously that's going to be a decomposition. We've seen this one before, one of my favorites. Sodium hydrogen carbonate is baking soda. It's what we call a mixed salt. Sodium, hydrogen, +1, carbonate, -2. So, the charges add up to 0. Charges cancel if you like, +1, -2. Decomposition. So basically when we do decomposition, you may remember this is the fire extinguishing gases in our experiment. Okay. When you heat it up, just put a little triangle there, that means heat, right? Well, a triangle means change. It changes when you heat it up. Turns into sodium carbonate. Now be careful here because sodium's a +1, carbonate's a -2. So we need 2 +1s. Okay, and that is a solid plus water, H2O. In our experiment that was a gas, so why not put it as a gas? And CO2. Okay. Let's do the balancing. So 1 sodium, 2 sodiums. 2 sodiums. 2 hydrogens, 2 hydrogens. There we go. 2 carbons, because there's 2 molecules, remember. So 2 carbons, 2 carbons. 3 oxygens inside, 2 molecules, 6 oxygens, 1, 2, 3, 4, 5, 6. So just with that simple 2 there, everything else is a 1. That's balanced. Okay. This is going to be a single replacement. Oftentimes a metal will replace another metal in a compound. Okay, so here it's the reaction of copper metal. Copper is Cu from the periodic table, solid, copper metal, with aqueous silver nitrate. Remember, silver is a +1 ion, same as up there actually, isn't it? Okay, silver nitrate, +1, -1, turns into, careful now because this doesn't balance itself as we do it, so it turns into solid silver, which is AgS, plus copper 2 nitrate. Now remember what that copper 2 means. That means that guy there is a +2 ion, right? So nitrate's a -1, so we need 2 of them. Okay, solution, it says. Aqueous. All right, is it balanced? Let's see. 1 copper, yes. 1 silver, yes. 1 nitrate bag or packet, 1 molecular ion, but here 2. We've got to be careful. So I need 2 nitrates. So I need 2 molecules, each has 1 nitrate bag, 2 silvers, 1 copper, so that's it. Now here's interesting. When we have, this is a +1 ion and this is a +1 and a +2, when we have +1s and +2s or even -1s and -2s, we actually have 1s and 2s in the balancing numbers, so that's a little trick, okay? All right. Finally, neutralization. A double replacement, double swap, but it's always the same simple idea. So acid plus base makes salt, which is a neutralization, plus water. A salt is just an ionic compound, any plus with any minus. All right, so an acid, special. Hydrochloric acid is H plus on the front, Cl minus on the back. The base here is a trickier one, I've decided. So I've got calcium hydroxide. Calcium, if you recall, is a +2 ion. Hydroxide's a -1, so I need to scratch that. Now don't worry about doing 2 things at once. Just ask yourself, calcium's going to pick up chloride, so it's going to be calcium chloride. Calcium's a +2, chloride's a -1, so I need 2 of them. Other one is going to be H plus with OH minus. I'm going to write it like this, HOH. That's obviously water, isn't it? But if I write it like that, that's the big trick. I'm writing it in terms of the ions. Okay, so now let's balance the same number and type of ions. 1H plus, 1H plus. The H in HOH is the H plus. Cl, there's two Cl's, so I need two of these. Oh, then I need two H pluses. I've got two OHs, I got two OHs. I've got one calcium, I got one calcium. There we go. Trick with the ones and twos again. So, 2 HCl, 1 calcium hydroxide, 1 calcium chloride, 2 water. Well, obviously in the textbook you'll see that written as water, H2O. There you go. Alright. Now, I'm going to kind of leave this to the side. Okay, we'll come back and look at that as we go a little bit. But in each of these reactions, and let's kind of see it here, question says, what do you think makes each of those four reactions, quote unquote, go? What's the driving force in each case? So, you know, it's a simple kind of question in chemistry, but kind of a deep question as well. All right, what makes these reactions actually go? Okay, in the first one, aqueous reacts with aqueous to make solid and aqueous. Making of a solid. Turns out that solids are very stable. Okay, so we made a stable product. In the second one, we've made smaller molecules. Smaller molecules are more stable. Okay, here it's kind of a weird concept, but we see transfer of charge, transfer of electrons in real life. That makes molecules more stable. But the bottom line is, in each of these cases, we see the formation of products that are more stable. And that essentially is how nature works. Nature turns less stable things into more stable things. So, to answer the question, why do they go? When the potential or possible products in a reaction are more stable. Now when we say more stable, it means they have stronger bonds, right, keeping the atoms together, than their reactants. Reaction occurs. In big kind of obvious writing, making more stable matter. More stuff. Oh. Stronger bonds. So, when the potential, you know, what you might make, when the potential products in a reaction are more stable than the reactants. Let's go that again. When the potential products in the reaction, the things you could make if it works, are more stable, have stronger bonds than the reactants, the reaction occurs, the reaction happens. Nature loves stable. You're making more stable things. So in that first example, we kind of mentioned it already. What's our evidence? What's our evidence that this process creates more stable products? Well, we see a solid. Okay, so in number one there, we see the formation of a solid. So I'm going to write that. Formation of a solid. That's how you know the reaction happened. Before your very eyes in lab, you saw these solutions go milky or cloudy. That's the formation of very powdery solids. Okay. So the bonds in the solid are stronger than bonds in solution. Remember those ions are separate mobile ions, they're electrolytes. They're actually stuck to the water, aren't they, when they're dissolved? And then they bump into each other, they make more stronger, stable bonds, and they fall out of solution as a solid. And we see this in replacement reactions, usually double replacement reactions. Okay. Next one. We see a decomposition. We see the formation of smaller, stable molecules. Okay, so generally speaking, the smaller a molecule is, the more stable it is. Okay, so think of a wall. If you knock a wall down, what you get? A bunch of bricks, right? The bricks don't fall apart themselves because they're stronger and more stable. So smaller things tend to be more stable than larger things. So we see the formation of small molecules. Typically water, carbon dioxide, occasionally HCl will be formed, things like that. Okay, so small, stable molecules. Okay, we see this in decompositions and of course neutralization, where we always get water as a product. Acid plus base makes salt plus water. All right. Finally, number 3. Mentioned it in passing there. So when we have metals which have 0 charge reacting with ions which have a +1 in this case to make 0 charge and a +2 charge, that infers that electrons have moved. Okay, we don't want to get into the details there, but if you see ions and metals, single replacements always, okay, it means we've seen transfer of electrons. So transfer of electrons, it's kind of a more advanced topic for our later courses, but you should be aware of it. Transfer of electrons, let me move that up. Single replacement reactions. Now it's funny because if you go back to it just real quick, in a single replacement reaction we have a metal that's in this kind of metallic state and a metal in the form of an ion. Okay, more reactive metals lose their electrons. So copper actually is more reactive than silver, so it loses its electrons to make an ion, and silver gains those electrons. Okay, so bottom line is, if you see a metal and an ion turn into the opposite pair of ions and metals, that means electrons have been transferred. Okay. Now, moving further on, the reaction we're going to spend a lot of time looking at, or the reaction type we're going to spend a lot of time looking at, is the double replacements. Okay, so we'll do a simple word example first before we move on to things complicated by balancing and stuff like that. Okay, so we're going to write 3 kinds of reaction, okay, for one process, and they're kind of telling you the same thing, just at different levels of sophistication. Okay, we're going to do the standard balanced equation in the book. Don't know why they do this, but they call it the molecular equation. Hang on, let me turn my lights on here. I forgot to turn my lights on. That's better. Oh, apologies for that. I'm sitting here in the dark at home. All right, that's a lot better. Okay, so 3 ways you can write this. So the balanced equation, sometimes called the molecular equation, is just what we've been doing. Okay. The complete equation is all the details. So we're going to write the dissolved ions separately, as you would find them in a test tube, and then the net is just where all the action is. It's very much a summary. Okay, so we're going to do the same one we did before. Okay, swapping the partners. Okay, silver, nitrate, and sodium chloride. Okay, so remember how to do this. Okay, silver, nitrate, +1, -1. It's a solution. The reactants always have to be solutions so they can swap partners easily. Okay, that's why we dissolve things, so they can move around and find each other in a test tube. Okay, plus sodium chloride. +1, -1, +1, -1. Nice easy one to start. Now when we swap the partners, what do we get? Ag goes home with Cl. AgCl. +1, -1. This is actually a self-balancing equation, right? It's all 1, right? Just to start with an easy one. And sodium nitrate, +1, -1. Now if you remember before, I put state symbols there, but I haven't put them this time. Okay, how do we know which one of these is the solid? You can't tell just by looking, okay? You've actually got to kind of look it up, all right? So, question, it's an important question. How do we know which of the products, this one or this one, is the solid? Solids are always formed in these double replacements, okay? Bottom line is this: we have what we call a solubility chart. Okay, you have to look at the solubility chart, and if you want to look at your practice exams at the web page, they are available there as well, these charts, okay? So they're in the data sheet. All right, so here's the solubility chart. There it is. All right, so it's kind of a glass half empty, glass half full thing, okay? On the left, we look at things that are mostly soluble. So it's a good idea to put aqueous here, right? So generally speaking, anything, and this is all about what's on the back of the compound, all right? So nitrate on the back, the example we just saw was sodium nitrate, generally dissolve, aqueous. Chloride, bromide, iodide, all in that same column 7 in the periodic table, group chemistry, generally always soluble, and so is sulfate, okay? However, there are some exceptions, okay? Having said that, nitrate, no exceptions whatsoever for nitrate. Every single nitrate compound in nature will dissolve. Very interesting, right? If you ever want to dissolve something, turn it into a nitrate, it will definitely dissolve. It can be anything. Silver nitrate, copper nitrate, even uranium nitrate. That's part of how they separate uranium from its ore. Okay. Now, so if we look up here, silver nitrate, hey, all nitrate compounds dissolve, so aqueous, there it is. Over on the right, sodium nitrate, all nitrates dissolve, so I can put aqueous right there, okay? All right. Now, back to the chart. Maybe if I can squeeze this in so I can see it both at the same time. Oh, yeah, just about. Okay. Now, nitrates all dissolve, dissolved, dissolved, all right? Chlorides, bromide, and iodides are all the same, apart from these three. These three here are special. They're exceptions. So these guys, silver chloride, mercury chloride, and lead chloride will be exceptions. They'll be solids. Oh, look up here. Easy one first. Sodium chloride, sodium's not an exception. We know table salt dissolves, aqueous. However, look, silver is an exception. It's going to make a solid. So here, that is a solid. Now that's super, super important because this little state symbol, solid here, and aqueous in the products has to be assigned correctly. Otherwise, we have big problems later on, okay? Because the next type of equation needs that information. All right. Now, what we didn't look at yet is things that are generally insoluble. Insoluble means not dissolving, so solids. So things with carbonate on the back, chalk, for example, calcium carbonate, calcium phosphate is essentially bone, okay? And hydroxides, they're generally all solids. However, some exceptions, ammonium and group 1, so that's your sodiums, lithiums, potassiums. Sodium and group 1 are exceptions, so they'll be aqueous, okay? Similar down here, apart from hydroxides, has a couple more exceptions. All right, so we're always going to refer back to the table to double check. All right, so keep this on the side, and we'll come back and use it to help us here. Okay, so the question says, and feel free to kind of pause this if you want to figure it out yourself. Okay. So state which of the following are soluble, which will be aqueous, or insoluble, which will be solid. So let's do the first one. Hey, let me move this down. There we go. So if you remember, move down a bit more. Nitrate on the back. All nitrates are soluble, no exception, so that's an aqueous. This is from the just example a second ago. AgCl, well, Cl generally dissolves, but silver is an exception, so that's a solid. Lead chloride. Chloride generally dissolves, but oh, there it is, lead. Solid. Calcium hydroxide, used that one a minute ago. If you remember it from a previous example, that was aqueous. Let's just confirm.